All right, let's get started. So, here's our setup. We have a sphere. It's filled with mercury gas, and there's no way for the gas to escape. It emits radiation to a satellite. The satellite, at any position, will always have the same intensity, or receive the same intensity. We know that the first distance it sits at is at 500 meters for 10 minutes. We want to know how far does it sit at for some other time. We also know that the sphere is always in thermal equilibrium. So let's get started. Let's find the distance first. So the distance can be found by considering the fact that intensity is going to be constant. And then intensity is power over surface area. And then if it's a sphere, it's intensity over power over 4 pi radius squared. And then in this case, our radius is just our distance, so this intensity equals power over 4 pi distance squared. Knowing that intensity is constant, it's just one same value, which means we can relate P1 to P2. So we'll get P1 over 4 pi d1 squared is equal to P2 over 4 pi d2 squared. Well, we know d, but we don't know p. But we do know power can be rewritten as the area times the Boltzmann constant times temperature to the fourth. So we can rewrite this as alpha sigma T1 to the fourth over 4 pi D1 to the fourth equal to alpha sigma T2 to the fourth over 4 pi D2 to the fourth. Not to the fourth squared. What am I doing? Ugh. Long day. These cancel because they're all constant or coefficients. So what we're left with is T1 to the fourth over D1 squared equal to T2 to the fourth over D2 squared. Okay, well, we know D1 is 500 meters, but what are T1 and T2? Well, it's easy. T1 is the boiling point when the vapor becomes liquid. T2 is the melting point when liquid becomes solid. So the boiling point of mercury is 630 Kelvin, and the melting point of mercury is 234 Kelvin. So let's plug it in. T1 is 630 to the fourth over D1, 500 meters squared is equal to T2, 234 Kelvin to the fourth over some D2 meters squared. What we get is we can isolate this by putting D2 over here, inverting this. We get D2 squared, or D2, excuse me, is equal to the square root of 234 to the fourth over 630 to the fourth times 500 squared. And that gives us a result of D2 is equal to square root of 234 squared over 630 squared, to the fourth. 234 to the fourth over 630 to the fourth times 500 squared. And that leaves us with 68.98 meters. And looking at our sig figs, our smallest is 2 sig figs, so that leaves us with 69 meters as our D2 value. Okay, well, how do we find D2? Again, we just need to consider some ratios. Consider the fact that change in time is proportional to the latent heat over temperature to the fourth. Well, we know latent heat because we know what material it is, and we know the temperature is because we found them, or they're given to us because it's mercury, so we can just set delta T1 over delta T2 is equal to L1 over T1 to the fourth times T2 to the fourth over L2. Okay, now let's isolate T2. We're just gonna drop the delta just because I'm lazy. T2 is equal to, invert that, so it'd be L2 over L1 times T1 over T2 to the fourth times T1, right? Yeah. All right, so let's fill in the blanks here. T2 is equal to L2, which is the latent heat of fusion of mercury. It's 11.8 over the latent heat of vaporization. That's going to be 272 times T1 over T2 to the fourth, so that's 630 over 234 to the fourth times T1, which is 10 minutes. All these units cancel, we're just left with minutes. So we get T2 is equal to .79 minutes, and we are going to sig fig that down to just 23 minutes as our final solution.